What if Mars did not simply dry out, but lost the very atmosphere that made oceans possible? Billions of years ago, Mars was a radically different world. Today, its surface is cold, dry, dusty, and exposed to an atmosphere less than 1% as thick as Earth's. But its rocks tell another story. Ancient river channels, lake sediments, water-formed minerals, and even ripples that appear to have formed beneath waves in a shallow lake. So what happened to all that water? Here is where the story gets controversial. Scientists are confident that liquid water existed on ancient Mars. But whether Mars truly had a planet-spanning ocean like Earth is still debated. Some studies have identified geological patterns in the northern lowlands that are consistent with an ancient ocean, potentially covering a huge portion of the planet. Other research has questioned whether proposed shorelines actually formed at an ocean's edge. So the safest conclusion is not that Mars definitely had Earth-like oceans, but that ancient Mars had far more surface water than it does today. And that leads to the bigger mystery. Where did the water go? The answer begins with something you cannot see from the Martian surface: the atmosphere. Early Mars appears to have had a much thicker atmosphere than it has today. That atmosphere mattered because pressure and greenhouse gases can help keep liquid water stable at the surface. But Mars had a serious disadvantage. It is much smaller than Earth. That means Mars cooled faster as its interior lost heat. And as its interior cooled, its global magnetic field weakened and eventually disappeared as a planet-wide protective shield. Now comes the part that sounds almost unbelievable. The sun itself helped turn Mars into a desert. The solar wind is a continuous stream of charged particles flowing outward from the sun. Earth is protected from much of this interaction by its global magnetic field. Mars does not have that same planet-wide shield today. NASA's MAVEN spacecraft has directly studied what happens next. Particles from the solar wind interact with Mars' upper atmosphere, helping remove atmospheric ions and gradually eroding the planet's gaseous envelope. During powerful solar events, that loss can increase dramatically. Over immense periods of time, even a slow leak can become catastrophic. But there is an even stranger process. It is called sputtering. Imagine the upper atmosphere as a thin layer of particles sitting at the edge of space. Energetic particles interacting with the atmosphere can knock other atoms out, launching them away from Mars. Not millions of years, billions. MAVEN measurements of argon isotopes gave scientists an extraordinary clue. Because argon is chemically unreactive, scientists can use its isotopes as a kind of atmospheric fingerprint. MAVEN data indicate that roughly 65% of the argon originally present in Mars' atmosphere was lost through sputtering over the planet's history. The same research indicates that large amounts of other atmospheric gases, including carbon dioxide, were also lost. And this is where water enters the story. Water is made of hydrogen and oxygen. When water reaches Mars' upper atmosphere, ultraviolet radiation can help break water molecules apart. Hydrogen is extremely light, so some hydrogen can escape Mars much more easily than heavier atoms. MAVEN has actually measured hydrogen escaping from Mars. The escape is not constant. NASA found that hydrogen loss changes with the Martian seasons, with escape rates increasing when Mars is closer to the Sun. During the strongest periods observed, the rate varied dramatically. So Mars did not necessarily lose its water in one gigantic event. It was more like a planetary leak. Some water escaped to space. Some became trapped in minerals. Some remains frozen beneath the surface and in polar deposits. And some may have moved repeatedly between the atmosphere, surface, and subsurface. NASA research published in 2015 used atmospheric water measurements to estimate that ancient Mars may have possessed enough water to cover much of the planet in an ocean at least comparable to, and potentially larger than, Earth's Arctic Ocean. That study estimated that Mars lost about 87% of that ancient atmospheric water to space. But this should not be interpreted as meaning every drop of Mars' original water disappeared into space. Water can also become stored in the crust and polar regions. Now here's the twist. Losing water was probably not the only problem. Mars was also losing the atmosphere that helped keep water liquid. As atmospheric pressure fell, stable liquid water became increasingly difficult to maintain at the surface. Temperatures dropped, evaporation became easier, and water increasingly became ice, vapor, or chemically bound inside rocks. The planet entered a vicious cycle. Less atmosphere meant a colder, less hospitable surface. A colder surface meant less stable liquid water. Less surface water meant fewer mechanisms capable of reshaping the landscape. And the Mars we see today gradually emerged. But ancient Mars may not have been the warm paradise we sometimes imagine. Recent evidence from NASA's Curiosity rover has complicated that picture. Curiosity analyzed carbonate minerals in Gale Crater and found extremely heavy carbon and oxygen isotope signatures. The results point toward intense evaporation and suggest that some later ancient environments may have supported only temporary liquid water rather than a permanently warm, wet climate. In other words, Mars may have repeatedly shifted between wetter and drier conditions rather than simply transforming overnight from an ocean world into a frozen desert. And Curiosity has found another remarkable clue. Ancient lake deposits contain textures interpreted as ripples created by waves in shallow water. That means water was not merely frozen underground or present as occasional moisture. At least in some places and periods, liquid water existed on the surface long enough to leave a geological record. So the real mystery is not simply, did Mars have water? It clearly did. The deeper question is, how long did it remain stable? How extensive were those bodies of water, and could any environments have remained habitable long enough for life to emerge? Mars did not lose its oceans because of one single disaster. Its transformation was probably the result of planetary cooling, atmospheric loss, solar radiation, hydrogen escape, changing climate conditions, and water becoming trapped or lost over billions of years. And that makes Mars more than a dead planet. It is a planetary warning written in rock. Earth has a thick atmosphere, a global magnetic field, abundant surface water, and active geological systems that help regulate its climate. Mars shows us what a planet can look like after losing many of those protections. And perhaps the most fascinating part is that Mars is still holding evidence of its lost world beneath our feet, inside rocks that have waited billions of years for us to read them. If you want more scientifically accurate stories that turn the mysteries of space into something you can actually understand, follow for the next one. Now tell me, if Mars once had vast bodies of liquid water, do you think life had enough time to appear there? And could traces of it still be hiding underground today?